In this section, we will investigate the nature of the bonds between atoms and how those bonds determine important properties in compounds. We can categorize chemical bonds into three different types based on the elements involved. The first type is ionic bonds, which are formed between a metal and a nonmetal. Some examples of ionic compounds are sodium chloride and magnesium oxide. The atoms involved in a covalent bond are both nonmetals. Covalent bonds are in carbon dioxide and diatomic nitrogen. In this course, we'll mainly focus on ionic and covalent bonds, though we'll take a brief look at metallic bonds. These are formed when metal is bonded to metal, such as copper or aluminum. Note that this is a simplified summary of chemical bonds because the bonds between atoms in most chemical compounds have varying proportions of both ionic and covalent characteristics. We'll take a closer look at the different types of bonds, beginning with ionic bonds. An ionic bond is the electrostatic attractive force between the oppositely charged ions produced when a metal atom transfers one or more electrons to a nonmetal atom. They form between two atoms with large differences in their ionization energies and electronegativities. These combinations typically occur when large metal atoms on the far left side of the periodic table, such as from groups 1 or 2, combine with smaller nonmetal atoms on the far right side, such as from groups 16 or 17. Here we can see the electron transfer from a sodium atom to a chlorine atom, illustrated with Bohr diagrams. These elements are located at opposite ends of the third period of the periodic table, so they exhibit significant differences in size, ionization energy, and electronegativity. The large sodium atom loses the only electron in its third energy level, becoming a smaller, positively charged sodium cation. The relatively small chlorine atom gains an extra electron, becoming a larger, negatively charged chlorine anion. Of course, when any macroscopic sample of chlorine gas and sodium metal react together, there won't be only two atoms reacting. Countless oppositely charged ions will be formed, which are drawn into an ordered solid, three-dimensional array of anions and cations, known as a crystal lattice. The chemical formula for the compound is the smallest whole number cation to anion ratio in the structure, which is 1:1 in the case of sodium chloride. The vast number of interionic forces present in the lattice locks the ions into place, which helps explain why ionic compounds are solids with high melting points. For instance, sodium chloride melts at 801 degrees Celsius. Different crystal structures of ionic compounds exist, which depend on the relative sizes and ratios of their ions. The ratios depend on the charges of the ions in the compound. Common ion charges are shown in this table. Recall that these elements tend to form stable ions by losing or gaining sufficient electrons to become isoelectronic with the nearest noble gas. Iso means same, so isoelectronic means having the same electron configuration. Lattice energy is the change in enthalpy required for the formation of an ionic compound from its constituent ions in the gaseous state. This is something that can be used to estimate the strength of the bonds in an ionic compound, which is of course going to be proportional to the force of attraction between the different ions. Coulomb's law says that the force of attraction between oppositely charged particles is equal to some constant k times the product of their charges, q1 and q2, divided by the square of the distance r between the two particles. The lattice energy can be defined as a sort of modified version of Coulomb's law, where U represents the lattice energy or potential energy. You can get the force formula by taking the negative gradient of the lattice energy formula, though don't worry about what that means since it's well beyond the scope of this course. Just knowing these two equations and being able to use them in explanations is enough. For instance, if we increase the charges or decrease the distance between the ions, we see that the magnitude of the force of attraction and the lattice energy will both increase. In other words, the ionic bond would be stronger. If the charges were smaller or the distance was increased, then the ionic bond would be weaker. As an example, we can compare the melting points of magnesium sulfide and sodium chloride. Looking at the charges, we see that the sodium and chloride ions have +1 and -1 charges respectively, while the ions in magnesium sulfide have +2 and -2 charges. Because of this, the force of attraction and lattice energy will be smaller in magnitude for the sodium chloride, so sodium chloride will have a lower melting point. A lower melting point occurs because less energy is required to overcome the ionic bonds. We also want to make sure we take a look at the distance r before coming to a final conclusion. We observe that sodium, chlorine, magnesium, and sulfur are all in period 3, so the sizes of sodium and magnesium, as well as those of chlorine and sulfur, are very similar. Hence, the difference between the r's in this example is not that significant. Now we'll do just a quick summary of ionic bonding by reviewing several points. First, ionic compounds form between metals and nonmetals whose difference in electronegativity exceeds 1.7. By the way, electronegativity difference is often abbreviated as delta En. These compounds usually form when metals from groups 1 or 2 react with nonmetals from groups 16 or 17. During the formation of an ionic bond, metal atoms will transfer one or more valence electrons to more electronegative nonmetal atoms. Ionic compounds form structures known as crystal lattices. Finally, the formulas for ionic compounds represent the smallest whole number ratios of cations to anions that are electrically neutral. Next, we'll take a look at covalent bonds. Recall that atoms consist of a negative cloud of electrons surrounding and attracted to a positive nucleus. The same electrostatic forces of attraction and repulsion within atoms, which influence properties such as atomic size, ionization energy, and electronegativity, play a role whenever atoms bond together. Bond formation begins with atoms colliding. To illustrate this, we'll look at two hydrogen atoms. When the two atoms approach each other, all of the electrostatic interactions associated with equally and oppositely charged particles occur. Repulsive forces exerted by the negative electron clouds and the positive nuclei of each atom slow the approaching atoms, converting some of their kinetic energy to potential energy. Additionally, the nuclei of each atom are attracted to the other atom's outer electron cloud. As they approach each other, the atom's electron clouds may overlap enough to cause the attractive forces to exceed the repulsive ones. The two valence electrons will move into the region of space between the nuclei, since this is where they experience the most attractive force from those two centers of positive charge. The force of attraction of the shared pair of valence electrons between the two adjacent nuclei constitutes a single covalent bond. In this example, the result of this covalent bond was a diatomic molecule of hydrogen. More generally, when two atoms of the same element form a covalent bond, the electron charge cloud density is greatest in the region of space halfway between the nuclei. For instance, if the two atoms are the same, then the electronegativity difference is 0, and on average the pair of bonded electrons will spend the majority of their time equidistant from the two nuclei. Although both ionic and covalent bond formation involve only valence electrons, there are several important differences to note. Covalent bonds typically form between two nonmetal atoms rather than between metal atoms and nonmetal atoms. The species involved in ionic bonds are ions, but because no electron transfer occurs in covalent bond formation, no ions form, and all of the species prior to and following covalent bond formation between two atoms are electrically neutral. The force of attraction in an ionic bond is between a cation and an anion, while in a covalent bond it is between a pair of electrons and two adjacent positive nuclei. Also, note that electrons in covalent bonds are nearly always associated into pairs. There are a few exceptions to this, such as dinitrogen tetroxide, a dimer formed by nitrogen dioxide. Finally, ionic compounds exist as large crystal structures while covalent compounds often exist as independent molecules. In between the two extreme cases of bonding we've examined, complete electron transfer and completely equal electron sharing, there is the case of covalent bonds involving unequal electron sharing. When atoms with different electronegativities form covalent bonds, the difference in their electronegativities may be minimal or significant. If delta En is less than 0.4, the bonding electrons between the two atoms spend no more of their time nearer one nucleus than the other, and the bond is designated as being mostly covalent. We might also say that the bond has very little ionic character. When delta En is greater than 0.4, the pair of bonding electrons will be drawn closer to the nucleus of the atom with the higher electronegativity, resulting in a bond dipole. As delta En increases and the bonds become more and more polar, the amount of ionic character in those bonds increases. A delta En in the 0.4 to 1.7 range is polar covalent, and a delta En greater than 1.7 is ionic. Note that the electronegativity differences in this table are a bit arbitrary. These bonds actually exist as a part of a bonding continuum, so the lines of separation between the different types are a bit more blurry than the table makes it seem. As an example of a polar covalent bond, we can look at an atom of hydrogen bonded to an atom of chlorine. Delta En equals 0.9, using a value of 2.1 for hydrogen's electronegativity and 3.0 for chlorine's electronegativity. We see that the electron density will be concentrated near chlorine, giving that end of the bond a partial negative charge and leaving the hydrogen end with a partial positive charge. The bond dipole can also be indicated with an arrow such as this, which is facing in the direction of the highest electron density, or the negative end of the bond dipole. Now we can step things up a bit and look at the case where atoms can form more than one bond. In the cases we've examined so far, only one electron has been required to achieve a stable outer electron shell and have all the valence electrons paired, but nonmetals sometimes require more than one electron. For instance, oxygen needs 2 electrons to achieve the valence electron configuration of the nearest noble gas, neon. The number of electrons required by an atom to achieve the stable outer electron configuration of the nearest noble gas, or in other words become isoelectronic with the nearest noble gas, represents the number of covalent bonds that the atom must form. Looking at the groups of nonmetals, we can predict how many electrons are needed to achieve a stable octet, and thus how many bonds must be formed. We should now take a moment to practice actually writing down formulas for these different types of compounds, and we'll do it via an example. Here we need to pair up the elements strontium, fluorine, and nitrogen to write the formula for the types of compounds identified below. Then we justify our choices by showing the appropriate delta En value next to each formula. The electronegativities of strontium, fluorine, and nitrogen are 1.0, 4.0, and 3.0 respectively. First, we need to write down the formula of a compound with an ionic bond. We know we need a metal and a nonmetal for an ionic compound, and strontium will be our metal since it is the only metal we are given to work with. We could choose either fluorine or nitrogen as the nonmetal since the electronegativity difference will be greater than 1.7 for either case. Here we'll just choose fluorine. We've started by writing the ion charges and then crisscrossing them to form a neutral ionic compound. Note that the metal is on the left and the nonmetal is on the right. We can show our calculation of the delta En value, which ends up being 3.0, to justify our choice. If you would like to convince yourself that strontium nitride would also be a correct answer, you can calculate its delta En value as well, though the numbers involved here make it especially straightforward to do. Next, we'll write the formula for a compound with a nonpolar covalent bond. Both fluorine and nitrogen are nonmetals and exist as diatomic molecules, so either would be a good choice for a nonpolar compound. Let's go with nitrogen. We can also show the calculation of the delta En value, which is just 0 because both nitrogen atoms have the same electronegativity. Just to reiterate, fluorine would also be a possible answer. Now we need to write the formula for a compound with a polar covalent bond. We really have only one option here, which is using fluorine and nitrogen. Nitrogen needs 3 electrons and fluorine needs 1. The element with the lower electronegativity, in this case nitrogen, normally requires the most electrons and is written first in a chemical formula. The process we're using here is similar to writing ionic formulas, except no charges exist and we don't always reduce the formula to the smallest ratio of atoms. This is because a covalent formula does not represent a ratio, and instead tells us the actual number of atoms that exist in the molecule. We then crisscross the numbers and delta En ends up being 1.0. Since this is in the range of 0.4 to 1.7, we have a polar covalent bond. Recall that ionic compounds are solids at room temperature and have high melting points. On the other hand, covalent compounds usually exist as individual molecules and in any of the 3 states of matter, solid, liquid, or gas. However, we shouldn't jump to the conclusion that covalent bonds are any weaker than ionic bonds. When molecular covalent compounds melt, weak intermolecular forces between the molecules are overcome. In other words, no chemical bonds are broken, unlike for ionic compounds. This is why, for example, methane has a melting point of negative 182 degrees Celsius, which is very low compared to the 801 degrees Celsius melting point of sodium chloride. The melting point does not reflect the strength of the CH bonds in methane, or indicate that the bonds are weak compared to those in sodium chloride. The energy required to separate the bonded carbon and hydrogen atoms within the molecules is much more than that required to simply pull the molecules apart. Evidence of the strength of covalent bonds can be seen when looking at network covalent solids. These are held together by covalent bonds that extend throughout the entire sample rather than consisting of individual molecules. Melting a network covalent solid involves breaking all of the covalent bonds within what is effectively a giant molecule, literally as big as the sample. Shown here is a quartz crystal which has a melting point of 1550 degrees Celsius. In this case, the melting point does reflect the strength of the bonds in the compound. We'll now take a brief look at metallic bonding. Metallic bonding involves electron delocalization. What this essentially means is that we have a structure of cations surrounded by a sea of valence electrons. The valence electrons move freely from atom to atom and are not associated with any specific pair of atoms. An alloy is a metal formed by combining 2 or more metallic elements. Alloys retain all of the properties of a metal in the resulting material, like electrical conductivity and ductility, but their properties may differ from those of the pure metals. Such differences include increased strength or hardness. Like ionic solids, metals and alloys crystallize and form lattices. Alloys are generally classified into two different types, which have to do with their crystal structures. First, we'll look at substitutional alloys, which involve atoms of relatively similar size. An example is an alloy of gold and platinum, which is one type of white gold. Notice how some of the atoms of one of the elements substitute the atoms of the other element in the crystal structure. Another type of alloy are interstitial alloys, which form when one atom is much smaller than the other. This example is a gold-copper alloy, which is one type of yellow gold. Adding other metals to gold improves its durability and strength. Pure or 24-karat gold is notoriously soft and malleable. Adding other metals to produce a gold alloy makes the metal more rigid, and the addition of copper gives the yellow gold an attractive rose-colored finish. We can see that due to their smaller size, the copper atoms become trapped in the spaces called interstices between the larger gold atoms in the crystal structure. Because interstitial alloys have metal atoms inserted into the interstices between the pure metal atoms, the resulting alloy often becomes more dense and more difficult to bend or deform, while a substitutional alloy may retain a similar density to the pure metal and may be equally or more malleable or ductile. We've seen earlier that an atom's valence electrons are the outermost electrons. These electrons are the ones involved in chemical bonding and are thus the electrons that matter the most in terms of chemical behavior. In 1916, the American chemist Gilbert N. Lewis devised a system of representing the atoms of the elements based on the number of valence electrons they possess. Each element symbol is used to represent the nucleus and all of the inner electrons of an atom and is surrounded with a series of dots representing that atom's valence electrons. These electron dot diagrams are called Lewis structures. We'll start off by discussing Lewis structures for individual atoms and ions, and move on to Lewis diagrams for molecular compounds and polyatomic ions. Drawing a Lewis structure for an atom is relatively straightforward. Lewis structures for some elements are shown in this table. We write the element symbol and then the corresponding number of dots around it to represent the valence electrons. If more than 4 valence electrons are present, we begin pairing the electrons. The number in the ones place of the group number gives the number of valence electrons for the s and p block elements. For instance, nitrogen is in group 15 and has 5 valence electrons. What happens if we have ions? For metals, the number of dots represents the number of electrons that each atom loses when forming a cation. For nonmetals, the number of unpaired dots represents either the number of electrons the atom must gain when forming an anion, or the number of electrons the atom must share when forming covalent bonds. From this, we see that drawing the Lewis structure for monatomic ions is also pretty straightforward. Let's look at sodium and chlorine as examples. Sodium, a metal, has only one dot, so it must lose one electron to become a sodium ion. Chlorine has one unpaired dot, so it must gain one electron to become an ion. From the Lewis structures for the sodium and chloride ions, we see that the element symbol should be enclosed in square brackets with the cation or anion's charge written outside the brackets on the upper right. The main focus for any Lewis structure should be the stable octet. The octet rule essentially says that the main group elements tend to bond in a way such that each atom has 8 electrons in its valence shell, making it isoelectronic with the nearest noble gas. We see that the chloride ion here has 8 valence electrons. It might be a bit harder to see with the sodium ion, but we have to remember that it actually does have 8 electrons in the s and p orbitals below the valence electrons that were removed. There are a few exceptions to the octet rule to note, but we'll look closer at them later on. Now we'll finally take a look at drawing Lewis structures for molecules. We'll draw the Lewis structure for a nitrogen trichloride molecule while following a series of steps. Step 1 is to determine the total number of valence electrons in the molecule. We first determine the number of valence electrons in each atom and then add them all together. Nitrogen has 5 valence electrons while chlorine has 7, though we need to account for all 3 chlorine atoms. Multiplying the 7 valence electrons of a chlorine atom by 3 and adding it to nitrogen's 5 valence electrons yields a total of 26. Note that this is an even number, which is what you will generally see. While the vast majority of molecules possess even numbers of valence electrons, there are still a few cases where odd numbers can exist. Step 2 is to construct the skeleton of the molecule using lines to indicate single covalent bonds between the atoms. Each line represents a pair of electrons. To generate the most likely skeleton of the molecule, the following set of guidelines is very helpful. These are based on numerous empirical observations and hold true for the vast majority of molecules. At first they might seem difficult to remember, but they'll become more familiar with practice. If the general formula for the compound is of the form AXN, then the central atom, which is A, will be the one with the lower group number. This also usually corresponds to the lower electronegativity. Of course, no central atom will exist if only two atoms exist in the molecule. Next, hydrogen forms only one bond, so it doesn't achieve an octet. Fluorine atoms always form only one bond, and the other halogen atoms usually form only one bond. Exceptions to this occur if those halogens are central atoms and are bonded to other small halogens or to oxygen. Normally, oxygen forms two bonds and does not bond to other oxygen atoms, though pure diatomic oxygen and hydrogen peroxide are some exceptions to this. Nitrogen generally forms 3 bonds and carbon forms 4 bonds. Finally, when drawing skeletons, avoid creating rings or cyclic structures. Looking back at our nitrogen trichloride example, we see that there are more than 2 atoms, so a central atom exists. Looking at the periodic table to compare electronegativities might be a bit confusing since nitrogen and chlorine both have values of about 3.0. However, the formula is of the form AXN, so clearly nitrogen is the central atom A and the chlorines are the X's. We can draw single bonds between nitrogen and the 3 chlorine atoms for the skeleton. At this point, the relative orientation of each chlorine atom around the nitrogen atom isn't that important. What matters the most at this stage is that nitrogen is in the center and each chlorine atom is a peripheral or surrounding atom. Step 3 is to subtract the number of valence electrons used to construct the skeleton from the total number of valence electrons available from step 1. This allows us to determine the number of valence electrons remaining. The total number of valence electrons available that was calculated earlier was 26. And in our skeleton we have 3 bonds each containing 2 electrons. The result is we have 20 electrons remaining. For step 4, we assume that all the atoms in the molecule obey the octet rule, except hydrogen. We'll determine the number of additional valence electrons required to give all the atoms 8 valence electrons. Because each peripheral chlorine atom has only 1 bond and is therefore associated with 2 valence electrons, the 3 chlorine atoms each need 6 more electrons to complete their octets. The central nitrogen has 3 bonds and so has 6 valence electrons. That means we need 2 more electrons for the nitrogen. Adding these numbers together, the 6 times 3 and the 2, gives us 20. Step 5 is to compare the number of valence electrons available to the number of valence electrons needed. If those two numbers match, we will place the electron pairs where they are needed to satisfy the octets. Fortunately, our two numbers were both 20, so they matched, and we can place the valence electrons, starting with the ones on the chlorine atoms and then the ones on the nitrogen. Now's a good time to take a closer look at the octet rule because there are some exceptions to be aware of. If an atom does violate the octet rule, then it must be a central atom in the molecule, since a peripheral or surrounding atom must not violate the octet rule. This doesn't apply to hydrogen, which is associated with only 2 electrons in molecules. An expanded octet, which means there are more than 8 electrons, and it's also known as hypervalency, is only possible for elements belonging to the 3rd period or higher because only those atoms have access to d orbital electrons. Beryllium, boron, and aluminum atoms will often have incomplete octets such that only 2 or 3 pairs of valence electrons will be associated with these central atoms. Returning to our example, the final step is to check that the total number of valence electrons represented in the diagram matches the total number of valence electrons calculated in the first step. We have an electron pair on the nitrogen, 6 electrons surrounding each of the 3 chlorines, and 3 bonds containing 2 electrons each. This gives a total of 26, the same number that we calculated at the very beginning of this example. Therefore, this is our Lewis structure for nitrogen trichloride. Now we'll go over a series of examples to further illustrate the points we've gone over. The first is carbon tetrachloride. We begin by determining the total number of valence electrons. Carbon has 4, and the 4 chlorine atoms each have 7, giving us a total of 32. We draw the skeleton like this. Each chlorine atom is connected to the carbon atom via a single bond. Now we subtract the number of electrons in these bonds from the total number of electrons to see how many electrons we have left. Each of the 4 chlorines needs 6 electrons to have a full octet, and the carbon has 4 bonds, so it already has a full octet, meaning we need 24 electrons. Since the number of electrons we have left is exactly the number we need, we can go ahead and add them to the structure. Now we check to make sure the number of electrons in this structure is the same as the total number of valence electrons we initially calculated. You can count them up yourself if you want, it's good practice. You should get 32, which is the same number as earlier, so we are done with this Lewis structure. This next example is boron trifluoride. We'll start off as we did before by calculating the total number of valence electrons. The boron atom has 3 and the 3 fluorine atoms have 7, giving us a total of 24. The skeleton structure is relatively straightforward as before, with boron as the center. We calculate the number of electrons we have remaining, which is 18. Now, each fluorine needs 6 more electrons and we have 3 fluorine atoms. This adds up to 18 electrons for just the fluorine, so there are no electrons left for boron. This is okay, however, since boron is an exception to the octet rule. Here we are fine leaving boron with only 3 pairs of valence electrons, which are accounted for by the bonds. We fill in the electrons for the fluorine atoms and check that this structure indeed has a total of 24 valence electrons. When the covalent bonds between two atoms involve more than one pair of shared electrons, they are known as multiple bonds. Multiple bonds are stronger than single bonds since multiple bonds involve more attractive forces between two atoms. Some trends are illustrated here by the bonds between two carbon atoms. The bond order is the number of chemical bonds between a pair of atoms, while bond strengths are usually measured by the amount of energy required to break the bonds. As the bond order increases, we see that the bond energy increases and the bond length decreases. For our third example, we'll draw the Lewis structure of carbon dioxide. We get a total of 16 valence electrons and then proceed to draw the skeleton with carbon as the central atom. Only 2 bonds are needed to draw this, so we have 12 electrons remaining. However, we need 6 electrons to complete the octet of each oxygen atom and 4 electrons to complete the octet of the carbon atom, which is 16 electrons in total. We don't have enough electrons to complete the octets in this structure, but neither carbon nor oxygen is an exception. We can solve this problem by sharing more electrons in our structure. If we move a lone pair of electrons from each oxygen atom to be shared with the carbon atom, we'll be able to form a structure that works. We see that we have a double bonded structure where all 3 atoms have stable octets. While we sometimes discover that fewer electrons are available than needed to complete the octets of the atoms in a molecule, there are other times when there may be more electrons available than needed. Normally, this results in expanded octets associated with the central atom in a Lewis structure, which is what we'll find in this example. An expanded octet will only occur with elements whose atomic numbers exceed 14, as this is when the d orbitals become available. The total number of valence electrons in this structure is 36, and the skeleton has xenon as the central atom. There are 2 electrons in each of the 4 bonds, so we have 28 electrons remaining. To complete the octets, we need 24 electrons, 6 for each fluorine and none for the xenon atom. But this leaves us with a slight issue. What do we do with the 4 extra electrons? We first place the 24 electrons where they're needed in pairs around each peripheral fluorine atom. We then place the remaining 2 pairs of electrons around the central xenon atom, remembering that xenon can have an expanded octet, and can thus be an exception to the octet rule. It's in the 5th period of the periodic table with atomic number 54. This structure makes perfect sense since each fluorine has 7 valence electrons, and hence is sharing 1 electron, while the central xenon has 8 valence electrons and shares only 4, so 2 lone pairs are left over. As a final check, we verify all 36 valence electrons are accounted for in the Lewis structure. Let's now draw a Lewis structure for a polyatomic ion, in this example a carbonate ion. When totaling the number of valence electrons, we need to account for the charge on the ion. The charge is -2, which means we need an additional 2 electrons, and add 2 when determining the total. If we had a positive charge on the other hand, we would subtract the number of electrons equal to the number corresponding to the charge. A charge of +1 would mean subtracting 1 when calculating the total. The total we end up with here is 24. The skeleton is as shown, and we see that we have 18 electrons remaining, while we need 20 more. We are short 2 electrons, and there is no exception here, so we must add 1 more bond. By adding a double bond between one of the oxygens and the carbon, we can arrive at a number of electrons remaining and required which match. We then place the remaining electrons and ensure that the total used in the structure is the same as we calculated earlier. Also note that we normally enclose Lewis structures for both monatomic and polyatomic ions in square brackets, as shown here. If this represented the actual structure, we would expect that the 2 single carbon-oxygen bonds would prove to be longer and weaker than the double bond, but experimental data does not agree with this result. It seems that all 3 bonds appear to be equal in strength and length. They appear stronger than a single carbon-oxygen bond but weaker than a double bond, and also slightly shorter than a single bond but slightly longer than a double bond. It's as if the 2 electrons in the multiple bond have been shared equally or average between the central carbon atom and each of the 3 oxygen atoms. These electrons are called delocalized by chemists since they are spread out equally between all three pairs of bonded atoms, and not associated with any one pair. Because Lewis structures cannot properly show delocalized electrons, we need to draw resonance structures. These depict the double bond in each of the possible locations in a series of diagrams, and connect each diagram with a set of double arrows. Be aware, however, that the pair of electrons does not move around between pairs of atoms as the diagrams might suggest. This is just simply the only way to depict delocalized electrons using Lewis structures. As a final example, we will examine the case where we have more than one central atom. In these kinds of examples, we are given the basic skeleton and can then proceed with the remaining steps to generate the correct Lewis structure. Recall that carbon generally forms 4 bonds, oxygen forms 2, and hydrogen forms 1. Starting with the structure on the left, we ensure each atom has the correct number of bonds, in this case just by making the upper carbon-oxygen bond into a double bond. We also add the number of electrons required to complete all the octets. To the structure on the right, all we need to do is switch it to having a double bond between the 2 carbon atoms, and then each atom has the correct number of bonds. We don't even need to add any electron lone pairs. This is all we'll do with these for now, but note that you'll encounter many molecules like them when studying organic chemistry.